Hello, welcome back everybody. My name is Michael. I hope you're having a wonderful day so far. We are going to be jumping back into some computer science learning for today. Today is February 1st, 2025, so happy February to those who are here. Yeah, we're here a little bit earlier to help cater to our East Coast and international friends here on the channel. And we're going to be completing the problem set for this stream, or at least hopefully a couple of these problems um, for this week. Welcome. Hello, Mahan. Welcome in as usual. Awesome, back again. How are we doing out there? All right, you're going on. I got 1% on my mouse. I gotta plug in my mouse. Oh, shoot. Okay, I'll have to use my trackpad for a second here while my mouse charges. I didn't realize it was on 1%. My fault, guys. All right, so we are on problem set 4 of CS50X here. So hope you guys are having a wonderful day so far. Thanks so much for joining me. Happy Saturday. Let's get into this here. So we want to submit volume here. Okay. WAV files are common file formats for representing audio. WAV files store audio as a sequence of, quote, samples, close quote, numbers that represent the value of some audio signal at a particular point in time. WAV files store audio as a sequence of samples, numbers that represent the value of some audio signal at a particular time. Okay, so like a magnitude or an amplitude. WAV files begin with a 44-byte header that contains information about the file itself, including the size of the file, the number of samples per second, and the size of each sample. After the header, the WAV file contains a sequence of samples, each single 2-byte 16-bit integer representing each a single 2-byte 16-bit integer representing the audio signal at a particular point in time. Scaling each sample value by a given factor has the effect of changing the volume of the audio. Multiplying each sample value by 2.0, for example, will have the effect of doubling the volume of the origin audio. Multiplying each sample by half means you will have the effect of cutting the volume in half. In a file called volume.c, in a folder called volume, write a program to modify the volume of an audio file. Hello, Wingong. Hello, Garlic Jeans. I like that name, Garlic Jeans. That's fine. That's a cool name. Welcome in. I'm using my trackpad on my laptop right now because my mouse is almost dead. It's on 1% here, so we are having to use my trackpad for a second here. I need to. I should have. Yeah, I should have upgraded that more. Okay, so we're here. Let's go into a new folder here. Into CS50X, new folder, week 4. Okay, we're going to do new folder in week 4 called volume. And a new file in this called volume.c. Hey, Ryan, welcome in. How you doing? Did you already finish this problem this week? How's it going with your CS50X? Or did you transition to CS50P? Okay. Let's continue on here. All right, so for this problem, you'll extend the functionality of the code of the CS50 staff. Download the distribution code. Okay. Paste. Unzip. Remove volume.zip. CD volume. Remove. Okay, so we're in volume now. We can see what it has here. So we have volume C. Okay. All right, let's go through this. So modifies the volume of an audio file. We're including standard integer.h, standard io.h, and standard library.h. Number of bytes in a wave header. So we have a constant variable, which is an integer header size, which is equal to an integer size of 44. Okay, that's the header size. We have command line arguments, and we have char star, right, to represent the strings. Okay. Check command line arguments. If not equal to 4 command line arguments, print volume, input wave, output factor, and a factor. Or input wave, output wave, factor. So you have to have 4 command line arguments: the file, the input.wave, output.wave, and a factor. Open files and determine scaling factor. So file, we're going to, so we have file star input on this variable. So this is going to, this is a pointer. Using fopen. Awesome. Sweet, Ryan. So we have a pointer here, which if we remember right, the pointers, let's go to our notes. Okay. So remember, is a dereference operator access the element given an address used to declare as a pointer. When applied to a pointer in a printf, this peeks at what is at that memory location. Okay, so star input is the what is exactly going on in this line here? We're using fopen. What does the fopen do again? So these are file IO. So file open. Okay. So file open, use open the command line to argument. The second command line argument as read. Right? So open the second command line argue in read mode. And then, right, we save input as a pointer to that location in memory. Right, so file asterisk input is a pointer to the file location in memory. Right? Is that what that means? So the argv1 in this case has to be the input wave, right? So in this case, it's input.wave, because argv0 is the name /volume of the file. So because it says if input is null, meaning that that memory space is null. What did the null mean again? So malloc, memory allocation, a function that lets you pass in a number, my device, right? Null. The address 0 is returned when something goes wrong with allocating memory. So we call file input. So this is a pointer to the file location in memory. So this opens and reads, though, the data inside. And saves it as this. Am I on the right track? Am I saying this correctly? Let's look up this. Let's go file input equals f open argv1 in read, right? I am trying to break this down. Don't spoil it for me, but see if I am on the right track and help me get there. Hold on, no, it didn't really ask. Start by looking at file. So we're looking at file. What type of file? What type is file star? It's a pointer. So file star is a pointer to the location of the data in memory. Yes, file star is a pointer to a structure that holds information about an open file, including its location in memory, its current position in the file, and other metadata. Now, double check. Yes, what the typo. So it's input I mean, we could debug it, right? We could just go like this. So let's go like this. Let's go. Right here. Let's just say print f. Percent. How would you print this for a file? Percent f? I don't know. Okay, let's just keep moving here. So I want to ask it. So input variable will house the open file in memory. What would calling a print f2 input display? A memory address. Yes, the input variable store a pointer to the open file in memory. If you do printf p for pointer input, this will print the memory address where the file structure is stored. Okay. So input is is a memory address of the open file. Okay, so if input is null, print file cannot be opened. So that, okay, got you. File output, we open this output in write mode. So we create this file. Okay, cool. And we have a factor, which is a float, ATOF argv3. So we're opening the input file and opening the output file. We're reading the input file and setting the output file as write. And then we are determining a factor here is the argv of 3. But at of, what does the at of mean? Let's go to CS50X docs. At of, convert a string to a float. Okay, so let's convert a string to a float. Okay, so our to-do is copy header from input file to output file. Read samples from input file and write data to output file. Okay. Complete the implementation of volume.c such that it changes the volume of a sound file by a given factor. The program should accept 3 command line arguments. The first is input, which represents the name of the audio file. The second is output, which represents the name of the new audio file that should be generated. The third is factor, which is the amount by which the volume of the original file should be scaled. For example, if factor is 2.0, then your program should double the volume of the audio file in input and save the newly generated audio file in output. Your program should first read the header from the input file and write the header to the output file. Your program should then read the rest of the data from the WAV file. Your program should first read the header file and input and write the header file. Okay. So header size is 44 number of bytes. So we need to read the first 44 bytes of the input.wav, copy it and save it into the output file, basically. Your program should then read the rest of the data from the WAV file, one 16-bit 2-byte sample at a time. Your program should multiply each sample by the factor and write this new sample to the output file. You may assume that the WAV file will use 16-bit size values as samples. In practice, WAV files can have varying numbers of bits per sample, but we'll assume 16-bit samples for this problem. Your program, if uses malloc, must not memory leak. Okay. Understand the code in volume.c. Okay, this is the code, got you. Copying the WAV header. Your first to-do is to copy the WAV file header from input and write it to output. First, though, you'll need to learn about a few special data types. However, inside the file header called standard int.h are the declarations of a number of other types that allow us to very specifically define the size in bits and sign, signed, or unsigned of the integer. 2 types are particularly useful when working with WAV files. Unit8 underscore t, uint8 underscore t is a type that stores an 8-bit, hence 8, unsigned, non-negative integer, hence unit, which we can treat each byte of the WAV file. Int16t is a type that stores a 16-bit signed, positive or negative integer. We can treat each sample of the AutoWave file as an int16 underscore t value. You'll likely want to create an array of bytes to store the data from the WAV file header that you'll read from the input file. Using the uint8t type to represent a byte, you can create an array of n bytes for your header with the syntax like this. You're placing Okay. This one's interesting. So if we're going to do a header with the byte size, so right off the bat, we know that we can do this uint8_t header, right? And then we're going to input this header size constant variable up top. Like so, header size. Like that. So then recall that WAV file is exactly 44 bytes long. Okay, yeah. So fread header size 1 input. So look up fread here. Read bytes from a file. Standard I/O, prototype size T. This function reads data from a file that has been opened via fopen. It expects an input, PTR, which is the address of the first byte of memory to which to read the data, size, which is the size in bytes of the type, NMEMB, which is the number of those types to read at once, and stream, which is the pointer to the file returned by fopen. So we have fread pointer. So we need to read the header file. So fread, we want to read the pointer, address to the first byte in memory. So this will be wouldn't be argv header. We want to read header as our first byte in memory. Header, we take in a header size as the next value, which is the size, which is the address of the first byte in memory, which is to read data. So then the header size here, and they have an input value of 1 here, which is the number of types read at once. So they do a 1, and then they put in the input here, which is the stream, as a file return, right? Because that's the input here. Right here. So we read the header. We then say write header size 1 on the output. No, we do need our semicolons, right? So we read all of the data in header. going to take this. I'm going to go. I am having trouble understanding these few lines. There's a small typo in your code header side. Okay, yeah, whatever. Okay. So 1, uint8 header size declares an array of bytes. uint8t is an 8-bit unsigned integer, often used in raw data like header files. The size of the array is header size, which should be defined elsewhere. fread header size 1 and input reads header size bytes from input to header onto header. Okay, so that's why we're not saving this as a variable out front, is because it's taking the input, reading the size, this size I'm putting on header, and header happens to be the same size. Okay, then it's taking the values of header, writing them onto output. Reads okay, so fread reads header size bytes into header, input and onto header. 1 means it reads one chunk of header size bytes. Fwrite header size 1 output writes header size bytes from header onto output. Again, 1 means it's 1 byte a chunk. This code means a fixed size. Okay, it's a big helping for image processing. Header is your buffer. Yeah, okay. So header is kind of like that middleman that's like being written onto and written off of. Okay. So that's copying the header file. So now read samples from input file. And write outdated back to output file. So we need to do another fread here. So I want to read and write again. I need to read and write again. I need to have another, so your program should read one 16-bit value factor, 16-bit byte at a time. So we need to have a uint 16t, we'll say audio by how many byte size? Your program should first read the header input. Okay, gotcha. Your program should then read the rest of the data from WAV file, one 16-bit 2-byte sample at a time. Your program should multiply each sample by the factor and then write the new factor into the output file. It can be signed. Your program should then read the rest of the data, one 16-bit 2 sample time. may assume that WAV files will use 16-bit signed values. What does signed versus unsigned mean? Eight versus 16-bit signed versus unsigned values. Here's a breakdown of, 8-bit versus 16-bit. 8-bit can store 2 to the power of 8, 256 different values. 16-bit can store 65,000 different values to the power of 16. More bits allows for a larger range of numbers. Signed versus unsigned. Signed can be both positive and negative, uses two complementary representations. Unsigned only stores non-negative values, 0 and positive. Okay. So it's just 2 to the power of the number of bits. It's just for a larger amount of numbers that can be processed, or a larger number that can be processed. And it can be negative as well. And okay, so read. So we have audio file here, which is a 16-bit integer. And what kind of size do we want to have? Well, it has to be the size of whatever the input file is. In memory. Well, we don't want to rewrite the header file, right? We want to write everything but the header file. We want to be on the header file. Right, because the header is writing the first 44, bytes into the file. We want to skip over the first 44 bytes and write the rest. But how do you do this in C? That's the question. So in the right updated, your next to do is to read samples from input, update those samples, and write the samples onto output. When reading files, it's common to create a buffer in which you temporarily store data. There, you can modify the data, and once it's ready, write the buffer data into a new file. Okay, so audio is technically our buffer in this case, right? With a buffer for samples in place, you can now read data into it. So buffer for a single sample. We can read data. So we want to read not onto header. I mean, this one it really gives you the answers here. I don't want to give it given to me, but this really gives you answers here. Some hints. Okay, so we have a buffer size. We need to read every 16-bit chunk of data in this file. But why would you... My question, though, is... Every buffer size of int1. Huh. I'm just not really following like what this sizing, like I'm not that good at, I'm not that great yet at like bytes and bits and understanding what's going on with like sizing and stuff. So you create a buffer for a single channel. We need to read at the pointer the address of the first byte in memory which we want to read data. So we want to read onto buffer from on a buffer right? So we would have to use the address location the address of something, right? We don't, it's not a pointer to buffer, we need to use the address of buffer. We then need to give a size of the buffer. Not of the buffer, but we'll have to say, use that size of function like it's telling us here, of the int16 t. So this will read a size of 16 bytes, or 16 bits, sorry. In bytes, 16 bytes. No, it's 16 bits. 2 byte sample at a time. And then you say 1 chunk at a time on input. So it's going to read from input a single chunk size of 16 bits 1 time and save it onto the memory location of buffer. But we don't want to do this. We want to continually do this. So we'll say while you can continually read so buffer return value. If this function returns the number of this function returns the number of items read, which equals the number of bytes read when the size is 1. If an error occurs or the end of the file is reached, this function might return a value smaller than or even 0. So while it's not equal to 0, like that, so we're going to continually read 16 bits at a time and put that on buffer for the entire duration of input until we get 0. Right, we have this example here. So at this point where we have read the chunk, we've read the chunk. We just multiply it by the factor. So we say the buffer at that time in the chunk is multiplied and equaled by the factor. So this will read the first 16 bits, multiply it by the factor, and then we need to write it on 2. So then F write from the location of buffer size of int 16 t 1 onto output. Right? Yes. So then is that all? I mean, I kind of want to, like, what really is going on here? Like, I'm not really following the memory aspects. Like, this whole sizing of is it's still what's kind of vague for me. Like, I'm not really aware of what's going on under the hood, really. I'm kind of following, like, the opening of the file, right, and the reading of it, but the whole accessing certain memory or chunks is what makes it kind of difficult here. So what happens if I go make volume, go /volume input .wave output .wave 3. Okay, I guess, did that work? Can you play these without on here? Something worked. Your program. Okay, so open with audio preview. When you listen to audio like as download. Don't do that to me. Okay, and then input. I don't know, that doesn't sound that much different. Okay, let's try it. Let's check 50. Um, No. Ah. Reduces audio volume factor of 0.5 correctly. Make volume. Okay, so we are not doing this correctly. 0.5. Dang it. So we have int buffer, fread, buffer. There's your version. So we're reading. Unit 8. So this does not work. Um, Go to my finder here. I open with QuickTime Player. Brain. What was that? Was like what was that called? That is funny. Why isn't it reducing it? So this should be, if I call make volume with a factor of 2, download. Open with. So 0.5 is not working correctly. That was that file. Okay, so the 0.5 is really increasing it drastically. Why is it increasing it really a lot? So what happens if I just do it normally? So I just download, go to my downloads, input wave. Okay. So if I do it via 5, it'll get really loud. Download. Yeah, that's just louder. So then why, if I do 0.5, is it so if factor is less than 1, when trying to multiply a float against a uint 16 t, what happens? When multiplying a float by that, which is unsigned 16-bit, simply promote. So if you have x equals 1000, float is 2.5. Result is 2500.000. So this is taking the value and multiplying it by 0.5 here. Print f percent I percent f buffer backslash n. You get unsigned short. HU. Right, so it should be reducing these. So then let me go here. Command C. And V here. Let's print it here and see what happens. Okay, let's go up. It's going reduction, reduction, reduction by half, reduction by half, reduction by half. Right? So why is this playing louder? 1748 divided by 2 is 874. Perfect. So the reduction by half is working, right? So then why am I not appropriately getting the half volume? Okay, let's go here. Let's go to Mr. Debugger here. Let's say my program works for double volume, but not for having when printing the values of buffer before and after line 51, they are appropriately being reduced by half. Sounds like you're working on filter problem set. Let's try to figure this out together. You mentioned that your program works by doubling, but not for halving. Can you walk me through your code? Tell me what steps you've tried. So I do this. Here, like so. Let's take a look at, you mentioned, thanks for sharing your code. Let's take a look closer. You mentioned that the values of buffer are appropriately reduced by half when you print them. That's a good sign. One thing to check is your data type buffer. You're using uint, which is an unsigned integer type. Which is an unsigned. When you multiply or divide, make sure your result fits within the range of this data type. If the result is too small or too large, it might not be represented correctly. Do you think this could be related to the issue you're seeing? I'm not multiplying by a negative factor. Let's just take like these. These are some of the prints output. As you can see, they are being reduced down by 0.5. Let's try to figure out why your alpha file isn't reflecting this change. One thing to check is that your data type of buffer, you're using uint16t, which is an unsigned integer type. When multiplying or dividing, make sure the result fits within the range of this data type. If it's too small or too large, it might not be represented correctly. What signifies being too large or small for a uint16t? The uint16t data type is an unsigned 16-bit integer, which means it can represent values of 0 to 6 to 5,005. Okay. 535. So 65,000. So there's one that's over. However, with what's going on here? Buffer is the wrong type. It needs to be signed to allow for. Okay. Buffer is the wrong type. The program should read the rest of the data. You may assume that WAV file will use 16-bit signed values as samples. uint equals unassigned integer. So int 16. Oh. Oh, I'm sorry. Okay, so that was literally it. Int 16. And then the header files can have unassigned, unsigned, or unsigned. So instead of uint 16t, use int 16t. Switching to int 16t could help if you're dealing with negative values, as int 16 can represent both positive and negative numbers. However, if your values is having, the data might not be the problem. Let's focus on the having issue. Yeah, I think that's the issue though. So unsigned means that it can be only positive. Ah, okay. So then why does the header file have unsigned? However, uint8t is a type that stores 8-bit, hence 8, an 8-bit unsigned, not negative, integer. So it has to be positive, hence uint. Int 16t is a positive or negative value. Okay. Interesting. I'm still not super comfortable with that exactly, but they did walk us through that one pretty like in terms of they had like a lot of the solution in the answer here, in the question here. Okay. What's my mouse at? 20%? That's good enough for me. I need my mouse back. All right. All right, submit this one of filter. Okay. So filter here. Perhaps the simplest way to represent an image is with a grid of pixels, dots, each of which can be a different color. For black and white images, we thus need 1 bit per pixel, and thus we could represent black and white, and could represent black as 0 as black and white as 1. In the sense then, this is in the sense then, is an image just a bitmap? Is an image just a bitmap, a map of bits of more for a more colorful image, you'll simply mean more bits per pixel. A file format like BMP, JPEG, or PNG that supports 24-bit color uses 24 bits per pixel. BMP actually supports 1, 4, 8, 16, 24, and 32-bit color. A 24-bit BMP uses 8 bits. Oh my gosh, the word bit is really getting annoying here. A 24-bit BMP uses 8 bits to signify the amount of red in a color, 8 bits to signify the amount of green in a pixel's color, and 8 bits to signify the amount of blue in a pixel's color. If you've ever heard of RGB color, well, there you have it. It's red, green, blue. If the R, G, and B values of some pixel in a BMP are, say, 0xFF, 0x00, and 0x00 in a hexadecimal, that pixel is purely red, as 0xFF, otherwise known as 255 in decimal, implies a lot of red, while 00 implies no green and no blue, respectively. In this problem, you'll manipulate these RGB values of individual pixels, ultimately creating your very own image filters. In a file called helpers.c in a folder called filterless, delete this, yeah. Okay, distribution code. Let's type this in. Okay, unzip filterless here. Okay, put this into our folder here. Delete. Okay, doesn't know where it's at. Okay, so this is filterless here. Okay. Execute ls by itself and make sure you see all the files and make file. You should also see a folder images with 4 BMP files. If you run into any trouble, follow these steps again. Okay, background. A bitmap more technical. Recall that a file is just a sequence of bits arranged in some fashion. A 24-bit BMP file then is essentially just a sequence of bits, almost every 24 of which happen to represent some pixel's color. But a BMP file also contains some metadata information like an image's height and width. That metadata is stored at the beginning of the file in the form of 2 data structures generally referred to as headers, not to be confused with C's header files. Incidentally, these headers have evolved over time. This problem uses the latest version of Microsoft BMP Format 4.0, which debuted in Windows 95. The first of these files, called bitmap file header is a 14 bytes. Bitmap file header is 14 bytes long. Recall that 1 byte equals 8 bits. The second of these headers is called bitmap info header. Bitmap info header is 40 bytes long. Immediately following these headers is an actual bitmap, an array of bytes, triples of which represent a pixel's color. However, BMP stores these triples backwards as BGR, which 8 bits for blue, followed by 8 bits of green, followed by 8 bits of red. Some BMPs also store the entire bitmap backwards with an image's top row at the end of the BMP file. But we've stored this problem set's BMPs as described herein, with each bitmap's top row first and bottom row last. In other words, were we to I just cannot stop yawning. I'm like, I can't stop. Oh boy, sorry. Can't stop yawning here. Okay, hold on. The first of these headers, called bitmap file header, is a 14 bytes long. Recall that 1 byte equals 8 bits. So 14 times 8 for total bits. The second of these file headers is called bitmap info header. It's 40 bytes long. Immediately followed by these headers is the actual bitmap, an array of bytes, triples of which represents a pixel's color. However, BMP stores these triplicates backwards as BGR, 8 bits for blue, followed by 8 bits for green, followed by 8 bits for red. Some BMPs also store the entire bitmap backwards with an image's top row at the end of the BMP file. Image's top row at the end, okay. But we store this problem set's BMPs described herein, with each bitmap's top row first and bottom row last. In other words, were we to convert the 1-bit smiley above to 24 bits, were we to convert the 1-bit smiley above to 24-bit smiley, substituting red for black, a 24 BMP would store the bitmap as follows, where 000F, F signifies red, F signifies white, where highlighted cells in red all instances of 00F. Okay. I can't stop yawning. Let me give me another some drink real quick. I can't stop yawning. It's taken me like 20 years to read this problem. I can't even get through it. So, oh. Okay. So, because we've presented these bits from left to right, top to bottom in 8 columns, you can actually see the red smiley face if you take a step back. To be clear, recall that a hexadecimal digits represents 4 bits. Accordingly, like FFFFFF in hexadecimal signifies this in binary. Notice that if you could represent a bitmap as a two-dimensional array in pixels, where the image is an array of rows, each row is a pixel array of pixels. Okay, this is getting. Come on, can we get to it here, please? What does it mean to have a filter an image? You can think of filtering an image as taking the pixels of some original image and modifying each pixel in such a way that a particular effect is apparent in the resulting image. Understanding. Let's now take a look at some files provided to you as distribution code to get an understanding for what's inside of them. The BMPH file. Okay. Open up BMPH as by double clicking on it and having a look. You'll see definitions of the headers we've mentioned. Bitmap file header, bitmap info header, in addition, that file defines byte, dword, long, and word, data types normally found in the world of Windows programming. Notice how they're just aliases for primitives, which we were hopefully already familiar. Got you. It appears that a bitmap file header and bitmap info header make use of these types. Perhaps most importantly for you, this file also defines a struct called RGB triple. Right here. That quite simply encapsulates 3 bytes, 1 blue, 1 green, and 1 red. The order, recall, in which we expect to find RGB triplicates actually on disk. Why are these structs useful? Well, recall that a file is just a sequence of bytes, or ultimately bits, on disk. But those bytes are generally ordered in such a way that the first few represent something, the next few represent something else, and so on. File formats exist because the world has standardized what bytes mean what. Now we could just read a file from disk into RAM as one big array of bytes, and we could just remember that a byte at array I represents one thing, while byte at array j represents another. But why not give some of those bytes names so that they can retrieve them from memory more easily? That's precisely what the struct in bmp.h allows us to do. Rather than think of some file as one long sequence of bytes, we can instead think of it as a sequence of structs. Okay, filter.c. Now let's open up filter.c. This file has been written already for you, but there's a couple of important points worth noting here. First, notice the definition of filters on line 10. Char star filters equals BGRS. The string tells the program that there's allowable command line arguments to programs that are B, G, R, and S. Each of them specifies a different filter that we may apply to our images: blue, blur, grayscale, reflection, and sepia. The next several lines open up an image file. Make sure it's indeed a BMP file and read all of the pixel information into a 2D array image. So the next several lines open up an image file. Make sure it's indeed a BMP file and read all the pixel informations into a 2D array called image. So where is image? Scroll down to the switch statement. That begins on line 101. Statement that begins. Notice that depending on what filter has been chosen, a different function is called. If the user chooses filter B, the program calls blur function. If it's G, grayscale, R, reflect, and S, sepia. Notice too that each of these functions takes the arguments: the height of the image, the width of the image, and the 2D array of pixels. These are the functions you'll soon implement. As you might imagine, the goal is for each of these functions to edit the 2D array of pixels in such a way that the desired filter is applied to the image. The remaining lines of the program take the resulting image and write them out to a new image file. Helpers.h. Now take a look at helpers.h. This file is quite short and provides the function prototypes for the functions you saw earlier. Okay. Um, but note that right now the functions are missing. This part is up to you. Oh, helpers.h, hold on. Here, take note that the functions that each function, oh my gosh. Here, take note of the fact that each function takes a 2D array called image as an argument, where image is an array of height, many rows, each row itself another array of width, many RGB triples. So if the image represents a whole picture, then an image 0 represents the first row, image 0 represents a picture in the upper left corner of the image. Okay. The only difference between the filter less and filter more apparently is that one has a sepia filter and the other an edge detection filter. We'll have to get there when we get there then. But I'm not gonna lie to you guys. I'm like tired. Like my brain is just not supporting me here. Like can't even read through this problem. Okay. I need to take this off. Okay. Now open up helpers.c. Here's where the implementation of the functions declared in helpers.h belong. Note that right now the implementations are missing. This part is up to you. Finally, let's look at makefile. This file specifies what should happen when we run terminal commands like makefilter, whereas programs you may have written before were confined to just one file. Filter seems to use multiple files, filter C and helper C, so we'll tell them to make. We'll need to tell make how to compile this file. Try compiling filter yourself by going to your terminal and running make filter. And then you can run the program by doing this. Okay. Which takes the image at images/yard.bmp and generates a new image called out.bmp. Which yard.bmp, out.bmp. Yeah. After running the pixels through the grayscale function, grayscale doesn't do anything just yet though, so the output image should look the same as the original yard. Specification, implementation. Implement the functions in helpers.c such that the user can apply grayscale, sepia, reflection, or blur filters to their images. The function grayscale should... Okay. So we got to go to helpers.c and do these. Okay, so what do we need to do here? So in grayscale, convert the image to grayscale. We're given a void grayscale, int height, int width, RGB triple, image height, image width. Okay. So for grayscale images, we need to remove all of the color basically for every pixel in the array of image height and width. So RGB triple, let's go to the BMPH file here. No, not here. Filters.c. Bitmap finder. RGB triple, image width. Calloc height, width, size of RGB triple. If image is equal to null. Okay, padding. So how can you... So that's our question now is, given the RGB triple of this image, so let's get some advice on grayscale here. One common filter is the grayscale filter. Oh, you guys can't read this. Okay. One common filter is the grayscale filter, where we take an image and want to convert it to black and white. How does that work? Recall if the red, green, and blue values are all set to 0x00 hexadecimal for 0, then the pixel is black. If all the values are set to 0xFF hexadecimal for 225, the pixel is white. So long as the red, green, and blue's values are equal, the results will be varying shades of gray along the black and white spectrum, with higher values meaning lighter shades closer to white, lower values meaning darker shades closer to black. So to convert a pixel to grayscale, you just need to make sure the red, green, and blue values are all the same. But how do you know what the values to make them? Well, it's probably reasonable to expect that if the original red, green, and blue values were all pretty high, then the new value should also be pretty high. And if the original values were all low, then the new value should also be low. In fact, to ensure each pixel of the new image still has the same general brightness or darkness as the old image, you can take the average of the red, green, blue values to determine what the shade of gray in the new pixel might be. So this is it gives us some what's it called here, to try to use. So we need to loop over all pixels. We need to take average of red, green, and blue, and update pixel values. Okay. Okay, so we need to do this. So I'll have to say we have to loop over all the pixels. So for int I equals 0, height, well, I is less than height, continually increase I, right? Oops.
I'm going thrifting. Should I take your car?
Sure.
Is that okay?
Yeah.
I was going to take mine.
All right.
Come on. It's working.
All right. So we're going to loop over, and then we're going to say height by width for int j equals 0. J is less than the width. J plus plus, right? What do we want to do here? We want to loop over both the height and the width, and we want to access the image at that place, right? So take average of red, blue, and green. So what are the values, though, at these individual points? That's what I don't get. So let's go to filters.c. So image height, width. RGB triple. What is housed at these locations? That's what I'm trying to figure out. So we close, we free the image. Size of bitmap file header. Control click on RGB triple to check the definition. Okay. So here we have a byte for RGBT blue, green, and red. And so a byte is just a value then of 16. So the RGB triple structure describes a color consisting of relative intensities, red, green, and blue, adapted from this. So the higher the byte size, the more intense the color of blue. So take the average of red, green, and blue. So average intensity, average whatever, pigment is equal to so we have this is going to be float, average pigment, so we have image index I and index j dot red RGBT blue, RGBT green, RGBT red. Plus image right image RGBT green plus image RGBT red. Like that. And then we need to divide this by 3 to give you an average pigment, right? Now, that'll give you an average pigment. Now, is it a float? Okay. So then we need to update the pixel values at this point too. So then we need to say image at index I and index j dot RGBT blue is equal to average pigment and we do this twice for the green and the red. right? So we just set each of those to that intensity. And that'll take care of those 2 points. We'll tell you access arbitrary values. We'll give you access to green values and so on. Okay, so we want to actually this is going to be an integer because we're taking a floor integer and floor here of 3. No, wait. When you compute the average, keep in mind the values of pixels RGBT red, green, and blue components are all integers. So be sure to round any floating point numbers to the nearest integer when assigning them to a pixel value. And why might you want to divide the sum of these integers by 3.0 and not 3? Anyone know why you would want to do this? Why would you want to divide by 3.0 and not 3? Okay. So I think that'll work for grayscale. Is there a way to make filter? Int average pigment. Oh, pigment. Woo! Yeah! Nice! Okay, so cool. All right, we got the grayscale one to work. Um, by 3 forces an integer, 3.0 is a float. 3.0f is a float, so keep the accuracy of the number. To get the decimal part, then you can use some function to round it, like round from math h, because they want you to round, not truncate it, I think. So we would so then what's going on in this 1.2k subs? We at 1.2? Thank you guys so much. Oh, we're almost there. We're 5 away. We're 5 away. If you guys are watching along and aren't subbed, we're 5 away from 1.2k. Thank you guys so much for joining me here. For those that are new, my name is Michael. I'm sorry I haven't introduced myself. I've been focused on the problem, but my name is Michael. I graduated college back in 2021 with a degree in human biology and a minor in chemistry. I work as a formulation chemist for a biotech company. I've been doing that ever since I graduated college, and I've been teaching myself how to code for the past 6 months. We're currently working on Harvard CS50X week 4, which is on in programming in C and just general computer science knowledge, and of course just helping us get into this realm. We've already taken Harvard CS50P, which was our first introduction to programming. We did that last summer, the summer of 2024. We completed over the course of that summer and then started the channel right after that and have been documenting our progress, coding every single day from then on forward. So I really appreciate you guys joining me here And if it's something that sounds like interesting to you or something that you enjoy doing or are in a similar boat, then consider following along here. We have a community growing here quite strongly, and it's really awesome. So we're taking average pigment. So he says 3O is a float, so it keeps the accuracy of a number to get the decimal part. But then by declaring integer here, let me hold on. What happens if I printf %i for right? So what happens if I make this guy? I always forget. Any standard IO. Okay, so it's printing whole numbers here, not floats. So then if I change this to 3, whole numbers, not floats again. With 75, 24, 18 being the last one. If I make this a float instead of an integer, what happens? I get percent F here. Float values. And does the output come out as grayscale? Yeah. So what's the difference then? I mean, we got in grayscale versus the other one. Is it just like a slightly different via decimal or not? I mean, the images are pretty similar, but it might just not pass check 50, right? Yeah, probably fail some check 50 checks by being off by 1. Yeah, let's try it. Let's run the check 50 for the grayscale and see what happens here. Reflect correctly in its own image. Grayscale correctly singles picture the whole area. Grayscale filter without being average expected is 28, not 27.66. So that's why it wants this rounding up to integer here. So if you floor by 3, what is actually going on? Like between the int floor 3, int floor 3.0, float 3.0. Just trying to do this. Okay. Not 27, so that's flooring it. Grayscale, it correctly filters more complex 3x3 image. Okay, so we need to round this up. So we need to keep this in float. Right? And then round the value up. So is there a round function here? Round in math.h. Yeah, I keep pulling this blanket over. Yeah, it's pretty cold. You guys can see outside. It's pretty like gray and gloomy. It's raining like crazy here in the Bay Area. So then we'll go int average pigment average. Round average pigment. So we equals. So we can't use the same name. So let's say average pigment like that. Let's check 50 here. Tim, you're gonna make me sound weak if I tell you the actual temperature. It's only 59 degrees here, so it's not crazy cold, but it's cold for what I'm used to. That's for sure. Okay, that handles all the grayscale. So we had to round it up. Put the calculation all in round. Okay, so that's a good idea. Let's just keep it as an int. And then just wrap the whole thing in round. He said, 59 degrees and you're complaining? What? Sorry, Tim. Don't hate on me. Don't hate on me, Tim. My bad. Then we'll need a parenthesis here as well, like so. Or not like on here. There. Like that. Cool, so that should work. Awesome, that's the grayscale done, guys. Woo! Moving up. Make sure we got the grayscale done here. My hair's all crazy today. All right, that takes care of the grayscale. Woo! Nice. Okay, let's keep going here. The sepia filter should take an image and turn it into a sepia version of the same image. So what is sepia? Are you looking for a sepia filter? Yes. What is it? A sepia is a warm brownish tone that gives a photo a vintage, old-fashioned look. It's originally used in early photography as a way to preserve images created by adding sepia pigments derived from cuttlefish ink to prints. Nowadays, sepia is often used as a digital filter to create nostalgic or antique effect, making images look aged and softened. What kind of pixel RGB manipulation can be done to achieve this? To apply a sepia filter through RGB manipulation, you transform the original colors by adjusting the red, green, and blue values. The common approach is using a weighted transformation of the RGB values. A basic formula for converting an image to sepia involves replacing each RGB values with these approximations. Okay, so it's the same thing. Okay, most image editing programs support a sepia filter, which gives an old-timey feel. An image can be converted to sepia by taking each pixel and computing a new red, green, value. There are a number of algorithms for converting images to sepia, but we'll focus on the following algorithm. For pixels of sepia color value should be calculated based on the original color values per the below. Okay, cool. So we'll take our for loop here, pretty much copy this entire code into here, into sepia. So we'll say we need to compute the sepia values here. So image index I and index j dot RGBT blue is equal to or we'll take this line here that it has, copy this in to here. Sepia blue is equal to this. But this is going to be image index I j dot RGBT red RGBT blue and RGBT green, like so, like that. Then we have sepia blue. Then we have sepia green, which is 0.349, sorry. Image RGBT red, 0.686 RGBT green, and 0.186 RGBT blue. Oh shoot, hold up. Blue, need a value here. Hold on, what's going on here? I need to drag this over. So 5. Let's take this. so image X J dot green like this. Boom. We'll set sepia green right is equal to this original red original green and original blue, like so. And then we got sepia red here, which will be original red, original green, and original blue, like so. Okay, we then set image RGBT blue is equal to sepia blue. RGB green is equal to sepia green. And RGBT red is equal to sepia red. But we need to define these values as ints like such. So now, if we go make filter, be green, make filter, do this guy up here, but instead of the grayscale, let's set this to sepia. I don't know if that's right. That looks funky. That looks really funky. That looks really weird. Uh-oh. 0.393 original red. 6186 189. Green is 349 original red. 686 original green. 186 original blue. And then in green blue is gonna be 272, 534, 131. Let's try to check 50 it, I guess. What do you guys think? We gonna get it right? Zeros for no, ones for yes? What do you guys think? Moment of truth here. No, sepia did not work. So we're off by one color, by one value. So it's the float thing happening again. Thank you, Vanch. I appreciate you. Tim believes. Appreciate. Hey, Vanch, how's it going? So float this guy. When you call around here. Like so. Let's see what that one looks like. No, that didn't work either. um, let's see what we get here. Tim's already let you down, my friend. Sorry, my guy. All right, let's see what we get here for this check 50. What do we get for this check 50? What do we get? 25, 22, 17, 65, 5. Expected 0, 0, 25, and 25. Of course, these results of these formulas may not be integers, but each value could be rounded to the nearest integer. It's also possible that the result number could be greater than 255, the maximum for 8-bit colored value. In that case, the red-green value should be capped at 255. As a result, we guarantee that the resulting values will be whole. Okay, so to compute the sepia value reasonable compute, round the result of each component to the nearest integer, ensure that the resulting value is no larger than 255. So what if it is larger than 255? So what if it is larger than 255? So if this value is 250, if sepia blue greater than 255, set sepia blue is equal to 255. Okay. Then do the same thing. Else if sepia green greater than 255, sepia green equals 255. If sepia red 255. Like that. Ah, nice. Woohoo! That looks awesome. I wonder who came up with all of these filter combinations. It's really quite interesting that we've like, if you think about it, filter processing was kind of like a chemistry back in the day. It still is with physical prints that you have to run like chemicals over them to achieve this various filter effects and things like that. And we've kind of been able to recreate that with code and with math is really crazy, right? Isn't that just bizarre? Like, really think about it. We're able to create and manipulate colors that we see with our eyeballs with math and numbers. It's just so bizarre. Imagine like the first time people put this together. Like imagine how crazy that would be. Sepia blue equals sepia blue greater than 255. All right, we got it. We got it. Cool. Sepia is done. Woo! Sepia done. Yeah, Vanch, like I really don't think people truly get like being a physical scientist in chemistry, like I kind of have been able to piece these things together about how crazy in reality these innovations are. And I think that's what kind of also drives my, my investment portfolios as well, is because I'm, heavy into tech and everything like that, just because I'm trying to get rid of the numbness to innovation. Like this is crazy, and this only happened, less than what, 50 years ago. So like, I mean, can you believe that? Like less than 50 years ago, or less than 100 years ago, we'll say for more intensive purposes, more inclusive purposes. Within probably your grandpa's or your great grandpa's lifetime, they were able to figure this stuff out without ChatGPT, without a lot of resources on the internet. So like what is my excuse? Like there is no excuse anymore to not try to figure this stuff out and not try to build upon it. It's like everything is there for you. If you're unwilling, it's just because you are unwilling and, lazy. Like it's just like, or just don't have a passion in it. It's just crazy. Like I took an image, I went over the image, manipulated each individual pixel using some sort of math, altered the color, and spit it back out. When normally I would have to have taken the picture on some big device, had that process out, dunked it into chemicals, had applied it in a red room overnight or over some period of time to not get impacted by UV light. It's just crazy. It makes it even crazier how they built these computers and think I don't even know how they came up with all of this. Yeah, exactly. Like that's why people say like, oh, like we're so much smarter than we were back in the day. Like, are we really though? Like on a person by person level, are we really smarter than our ancestors? Like in terms of, yeah, maybe the mass amount of general knowledge we know might be greater. We might know more about other nations now because we've had, internet and communication with them or whatnot, but niche expertise, were our ancestors smarter than, like, it just blows my mind. And hopefully you guys can also gain that perspective. Like when you really start to kind of open that that third eye, I guess, right, and see things for like against the kind of the mainstream media of how like you're just kind of going with the flow of everything and just taking at things as they come and not really thinking about where they truly came from, like all these products and stuff, but really try to take a step back or into these products and see, what went into making them. And it's just truly incredible how humans are. Yeah, exactly. We have more info at our fingertips, but are probably dumber. Exactly. Like, do you think that the amount of info at our fingertips is what has made us dumber? Has it served a counter purpose by providing us all this info that we've become, like I said, so numb to it? Like this is what I talk about with investing, like, and why I often tell people like I'm so gung ho on tech, even though like it is risky market, because at the end of the day, tech is the only thing that is rapidly improving like this. And what other industry besides maybe healthcare has been able to go over individual pixels and recreate these physical sciences with math and with computers? Like I mean healthcare now is technically just computers now. That's all healthcare is or will become. Like and pretty soon all of your medicinal formulation will all be computerized and will all be math based, and it'll no longer be trial and error via humans. It'll be crazy. You want to see my sepia code? Yeah, no problem. I got you here, Ryan. Here. So you have to do this 255. There's a note here that sepia can't be, the value can't be greater than 255. So that's what I had to do here and add this. But this is the code for sepia right here. Hey, Insomniac. Yeah, Jake Perkins, thanks for coming in and talking with me here. And Yeah, we have more. People now know how to find the answer. Back then, they actually learn the answer. Yeah, right. Exactly. Like, I mean, kind of cringy, but teach a man to fish versus give a man to fish. I feel like AI is the perfect example of give a man to fish. Whereas if I wanted to learn how to build a house or how or what went into it, I would have to go out and physically build the house to learn, right? Back in the day, or I had to if I wanted to learn how to, take apart an engine and put it back together. I went outside into my old beater car, took apart the engine and put it back together. I didn't go to ChatGPT and ask how I did it or how to or watch a video on it. So I think that physical, actual, just trial and error by actually learning by doing, it has kind of been lost. It's all about time savings, right? So you're trying to minimize the one off that path down that research might be a sunk cost. That's what I think everyone's fear is, which is not the way to go about it if you want to really learn. It's been more about memorization nowadays instead of actually learning stuff, especially in schools. Yeah. I'm a firm believer that if you cut off the internet, 99.9% of developers would not be able to do basic tasks. I mean, I'm guilty of this alone. I try my best not to use AI and other resources, but I still find myself having to, go ask it a simple question. Now, if I didn't have that tool and I had to go into my physical library, search through a glossary to find the specific code that I highlighted and made a note of in one of my textbooks, then that would be a whole nother, effort in itself and probably would help you refresh other memories trying to find that information. But because it's so accessible quickly, you just get that one thing rather than getting kind of that umbrella effect of everything within that category. AI is still only helping text and code, not in other domains much. Yeah. I really think, though, Insomniac, that AI into the pharmaceutical industry is going to be the next move. Now, don't quote me on this. I could be just blow up and be all completely wrong, but in my opinion, I think it only seems fit that AI will move into the biotech area and heavily start to, you know, manipulate and take over these pharmaceutical industries as they try to automate their formulations. At least that's from my point of view. Being in chemical formulation and having I applied to some jobs in medicinal manufacturing and chemistry. They're constantly everything they do is trying to cut cost. Everything that they do is trying to reduce lead time, reduce errors, reduce extra costs. So if they can implement AI into it, they are going to, and I think it's going to happen sooner rather than later. I've learned more through failure than searching on the internet for sure. Yeah, definitely, Jake. I mean, some of these problems that I've been working on, I struggled through, but by learning them, I mean, I was have been able to get through this two-dimensional matrixy because in the past week's problem set, we had to struggle through two-dimensional matrix. So now we're using nested for loops and accessing this image matrix really easily because it makes sense now. We have an image of columns and rows. We're accessing the right column by the left column, accessing that pixel, changing its values, and moving to the next one, to the next one, to the next one, right? I've often had to change machine learning algorithms based on human buying patterns, which is heavily influenced by economy and geopolitics. I think coding is the only thing that's very fixed. Yeah, pharma could leverage, but these would be unique skills, both chemistry and computer science. Yeah. Yeah, so maybe we're in the right boat then, Insomniac, being a chemist and potentially migrating into computer science. This might be a prime time for us then, to make this transition. If that's what we believe is, what's inevitable is, chemical manufacturing of, medicinal products via AI and research, then, this could be a meaningful path to travel down. We're right in that realm. Okay, cool. That was sepia. Now let's move on to reflect. So the reflect one, are we reflecting horizontally or vertically? So the thing is we need to override the pixel but save the pixel from before. So we have to use a temp variable. So let's say for int I equals 0, I less than the the height right, and I plus plus for int j equals 0, j less than width, j plus plus. Okay, we need to pretty much have the pixel temp equals to, so int temp is equal to the pixel at image I and j, right? We save that, and temp. We set image pixel I and j to equal, so to reflect an image, is this vertically or horizontally? I'm gonna think it means reflect it horizontally. So we need to move the not the height but the width to the negative position. So we have to divide the width in half. Find the halfway point and go beyond scale beyond that point. So image, if I is our height, I will stay the same and j has to change. So j would be what, plus 180? Flip 180 degrees. So image I at that height, but 180 pixels to the right. So you'd have to divide the width by 2 to get the midpoint. Minus middle. No, so you would just subtract from the middle. And then the difference, yeah, okay, so we go like this. Int middle is equal to the width divided by 2. So we save the temp image on our left side of the middle as the temp variable. Then we'll access the minus the difference. We need to know the difference to the middle. Is equal to middle minus j. So we have the middle, right? So this is what I'm trying to do here, whiteboard. We have an image here. We have some pixel here. I'm trying to put that pixel over here. So x0 is going to become x1. So I'm saving x0 in temp. Saving x0, and then I'm overwriting it as x1, right? So if the midpoint is here, the difference is this point here. So pixel minus, so middle minus j. And so then we need to go middle and plus difference. Oh, distance to the border would be a good one too, rather than doing middle. Right, that'd be a good idea too if you do distance to the border rather than middle. Okay, so let's think about it like that. If we do distance to the border, let's say you have a pixel x0 over here. X0 here, and we want to reflect x0 to over here, right? Well, the distance to the border is here, and that should be the same here, but just inward this way. But what signifies the border? The max width? Yeah, the max width. It signifies, so 0 on a width is the border. 0. So let's think here actually. So we save, we calculate width here is okay. So we need we know this distance here, right? This is just the width provided at this image. We know the entire distance. So we know then this chunk here. Horizontal. It's horizontal. Reflection. Okay. So we need to take the value. Find the midpoint relative to the midpoint. Okay, so we have this is the pixel that we're on. So let's say the pixel we're on is 0, 0, top left. We need to make this 0 width. So if it's negative, if it's 0 for height but has a width of 5, if the entire width is 20, we need to place this at the entire minus that one. Okay. Width minus j. No worries, Ryan. Appreciate you stopping by. So, right, well, that's what we need to, if we have the width of the entire picture, right? We have the entire width, right? This is the width. Okay, we know that this is the width of the individual pixel. So the difference between these two, width, this is j, basically. Width minus j would provide you this distance here. Width minus j. Okay, so hold on. If we have a pixel, and it's at 0, 1, 0 for height, 1 for width. It's slightly indented. We need to go width minus j, so back in 1. So if j is 5, so in this example, if at this point here, this pixel here at, let's say that the height is 3, the width is 4, right? 3, 4. We would go width, if the entire width, let's say, is 25, we would need to go 25 minus 4 to get to this pixel here. So that's why you do width minus j for the, so you save the temp as that value, as this value, this pixel. Then we save this pixel spot as whatever's in this position here. And then we save this position as the temp. Like that. Don't forget the -1 because the width will be 1 larger than your last index available. So 0, 0 isn't a pixel. You have to have 0, 1. So you're talking about a -1 right here. Oh, so this is RGB triple. Okay, so we make filter here, and then we do filter of reflect that looks right to me. I think the guy swapped places, right? Let's do make filter of that one. No. Dang. So this person needs to come over there, basically. So the image is at 0, at 1, 1. What are we missing here? So we're saving the current pixel in temp. We're then overriding the current pixel with the image, with the pixel that is 70, 80, 90. Then we override the current pixel with the pixel that is at. So then what if I just remove this part here? I don't know. Let's see. I'm just checking stuff. No, I didn't do anything. Oh, I'm only wanting to do this to half the photo. Right. So we're only wanting to do this on width divided by 2. Okay, so we're only wanting to do this on half the photo. So, right, because we're going to the other side and then we're doing the swapping it back, basically. So we need to stop when we reach a width that is equal to so while width no while so while I divided by 2. Yes! Woo! We already were accessing j, so we can just do width divided by 2 within our for loop to stop at j width divided by 2. Nice. So now this should work. Now we have that girl on the other side. Oh, I'm feeling it now, boys. We're moving. You know, you look like a younger version of Tom Wellington, Clark Kent. Is that Superman? Definitely not Superman over here with these string beans, but I appreciate the kind words. Thank you so much, and thank you, Jake, for that. Yeah. So what we did right is we were already iterating over j, so we can just make this stop at j to width divided by 2, rather than doing some third-party while loop, right? Encompassing this entire thing. So sweet. That solved reflect. Oh no, it didn't. Dang it, no. Oh shoot, it didn't solve it. Is it this -1? This does have some weird effect now on this left side, which I don't think is correct. No, so that didn't do it all. So yeah, we have to keep the -1 there for that bounding. So it's reflecting, but it's not. Is there some sort of bound here that we're missing? Let's see. Recall that lecture we implemented swapping two values with a temporary variable. No need to use a separate function. Over every pixel in it. There's some edge cases to consider here. So what if the width is what if the width is odd? Well, j is less than or equal to the width. It still does the reflection. Let's see if that does it. We'll go up to the width on cases of being odd and include the width. No. Any pixel on the screen on the right side, vice versa. In the reflect function, you'll need to swap the values of the pixels on opposite sides of a row. What are we missing here? There's some edge cases here to consider. I mean, our values are looking the same here. Anybody know what's going wrong here? Whoop. My bad. That could have been bad. Whoops. Let me grab a paper towel. Alright, there's a little bit of condensation from my glass. We're going to just clean it up. This goal to reflect this vertically as well, just horizontally at the moment. Yeah. My image reflects, but what is wrong? What is wrong? Anybody know? Um, hmm. It's checking small end case, edge cases by 1/2 image, 1/3 image. I don't reflect any of them correctly. Well, on this one, 00255 backslash n 255 0, I'm getting 00255 backslash n 00. Two 55 0 2. Shoot. Do I need to do the whole height as well? That's not equal to height. Oh, I get you. We're doing -1 here, so I have to have -1 here. You're right. You're right. You're right. Now we check this bad boy. Sweet. Boom. Okay. Sweet, that is reflect. So, Jay, can you explain to me why exactly we have to decrement by 1 here as well? So let's just say that your image, you're on pixel 0 for height, but 5 for width. So you're at, if this is your page, right? If this is your page, your picture, you're at 0 for height and you're at 5 for width. So your pixel's right here. So then you would take the width, subtract 5, and place that value here. Oh, because width starts from 0. So 0, 1, 2, 3, 4, 5. So technically it's actually on 4. So 5 would be the 6th value. So that's why you subtract 1 to get 1 more beyond for the 0 indexing. Ah, okay. Right, because if you start at 0 here and you're on pixel 5, well, that means you're actually at the 4th position in the array. And so if you're starting from the back, you would be, if you're at -4 here, well, that's actually -3 because it's -1, -2, -3. -1, -2, 3, -4. So we need to go -1 more to get to the -5th. Yeah, the 0 indexing. So, right, because this is a two-dimensional matrix which are being used with arrays, we have 0 indexing going on, so we have to keep that in mind. Because when we're starting from the back, if our width of the current pixel is 5, right, we would go width minus j. So if our width is 20, well, that would be 15. We need to go back 1 more, because it'd be -1, 2, 3, 4, because this is on the 4th index. Yeah. Sweet, that was reflect. All right, let's take a stab at blur here. Nice. Okay, blur. So blur, how do you do a blur? How do you do a blur? Give me a small hint about how to perform a blur when iterating over pixels. Consider averaging the color values of the pixel with its neighboring pixel to create the blur effect. Think of a grid, 3 by 3 centered on each pixel, where you compute the average of all the surrounding pixels and assign it to the center pixel. Think of a small, give me more. Please. Give me more, please. To blur an image, you can iterate through each pixel and apply a weighted average based on its neighbor. Here's how you can approach it. Loop through each pixel, handle the boundaries, calculate the average for each pixel, sum up the RGB values of its neighbors, including itself, and divide the total number of pixels by the neighborhood to get the average. Update the pixel, assign the average RGB value back to the current pixel to apply the blur. If you're using a 3 by 3 grid, you'd sum the colors from the 8 surrounding pixels. So do you find an average of all the pixels and apply that? There are a number of ways to create an effect of blurring or softening an image. For this problem, we'll use the box blur, which will be taking each pixel and for each color value, giving a new value by averaging the color values of neighboring pixels. Consider the following grid of pixels. The new value of each pixel would be the average values of all the pixels that are within one row and column of the original pixels, forming a 3 by 3 box. Okay, so you would access a pixel, find the box around it, and take the average of that and set it to this pixel. For example, each of the color values for pixel 6 would be obtained by averaging the original values of 1, 2, 3, 5, 6, 7, 9, 10, 11. Likewise, the color average values for pixel 11 would be obtained by averaging the color values of pixel 15. We were still 10, 11, 12, 14, 15, and 16. Copy image. And 3 by 3 and average them, yeah. So the thing is though, is we have, let's try it here. For int I equals 0, I less than the height, I plus plus, for int j equals 0, j less than the width, j plus plus, right? We can create, right? The thing is though, is if we override this image, it will be overridden in the next iteration. And so we don't want to take that average. We want to take the average of the original one. So we need to create a copy of the image at each point, right? So while j and while I and j are, while I is greater than 0, greater than or equal to and J is greater than so we need for these edge cases though, so I can't be 0 or can't be negative. So copy the image. While I is 0 and J is greater than 0, continually so we need to average, find the average of this copy. So if we're trying to find the average of the copy, so let's say that that copy is at 6, which is at 0, 1, 0, 1, 1, 1, right? 6 is at 1, 1. So this is at copy, this is at image 1, 1. We want to take the copy so we need to create a 3 by 3 square. So I will go up by 1 and down by 1, and so will J. So and then for J minus 1 to 1. So how can, if we have the 6 at 1 for height and 1 for width, we need to reduce I down by 1 unless it's 0. You can check that, get that value. So we need to go get all the values. We need to do another loop and loop over all the values around this point of time. So for I so while for I in the range of this is at 1, 1. We want to go to 0, 0, 0, 1, 0, 2. So I back by 1. For int k equals I minus 1. So k will be I minus 1. So if I is 0, can't do that though. Gets headache from studying coding problems, goes to watch someone doing coding problems. Hey Richard, thanks for coming in. Because the pixel you're checking is the middle of the 3 by 3 square. Okay. So we have a copy of this current pixel here. Why do we have to save copy? Index I, index J? Why can't we just say copy? Why can't we just say copy right here and set this equal to RGB triple? Like that. Copy. Well, I minus 1. Awesome, thank you. I appreciate you coming in, Richard. It's awesome that you were able to stop by today. We're almost done with this problem. I'll probably have to end it after this one because I'm going to go see a movie tonight with my girlfriend. We're going to go watch that new scary movie that came out. So, right, we're accessing each value. What do we need to do, right? What do we need to check? We need to loop again and gather the average of all the surrounding values at that point. So we need to loop and go from, so in the example of 6, which is at 1, 1, we want to go from 0, so I minus 1, to I plus 2, int k equals I minus 1. Up to, well, k is less than, so k is going to be 0 in this case, 1 and 2, less than 3, k plus plus, and for int L equals to, so then J, or the width, will have to be from 0, the same thing, from J minus 1 to all L is less than 3, L plus plus, okay. Now we're accessing all the values around this value, this copy. So then we need to say image index K and L dot RGBT red plus image K L dot RGBT blue plus image K L dot RGBT green no, we want to just assign this one. We want to get the average of all the red values of this one. So we get the red value here. So that means we're first going to get this one here. So if we're at the 6, 1, 1, we're going to have K equals 0, L equals 0. So we'll be here. We're going to get the red value here. When you get the red value from here, sum it, or because each square has 3 values, a red, green, and a blue. So we need to get the red value from this square. And do we need to add it to like a list? Or we'll just say red int red equals int red int blue int green. We're going to take the red plus equals image red blue plus equals image KL dot RGBT blue, and green plus equals image at K and L dot RGBT green. So we're getting all of the red, blue, and green values for that at this square. We're adding it to this one, and then we need to average it out. So the thing is, though, so we'll need a count here as well for every value you find. So technically it would be 9, 0, 1, 2. So if it was an edge case, it'd be count. So I'm not really sure what to do for the ones where like on the edges of the border. But are we down the right track here? What do you guys think? Within one row and one column. Edge, just add ones you have. What? Only 2, 5, 6. You should directly grab these indices, I plus 1, etc., if it's safe to do so. So then should we say while I is greater than or equal to 0 and j greater than or equal to 0, while so while I is greater than or equal to 0 and j is greater than or equal to 0, we will continually and I is less than 3 and j is less than 3. So while I is greater than or equal to 0, meaning that we'll go no reason for a while, just grab, okay. So if I if I is equal to 0, so if I is equal to 0 for height, and width is equal to 0 for the edge case, so while I is equal to 0 and h is equal to 0, no, if I is equal to 0 and h is equal to 0, meaning that we're in or I is equal to 0, no, sorry, j. So if I is equal to 0 and j is equal to 0, we're in a corner. Or I is equal to 0 and j is equal to width, right? Or I is equal to height, and j is equal to 0, right? Or on the bottom right hand corner, width, I is equal to height, and j is equal to width. So these are our 4 edge cases. For the corners, but what about for these ones? Okay, so this is edge cases for the corner values. If so okay. So edge case for the corner values. If I height does not equal to 0 and j else if so if height is 0 and j is so if height is equal to 0 and j for width is not 0, right? So, and I for height, so if the height is equal to not 0, and so if height is equal to not 0, meaning we have height, and j but what about the other case is on the other side where you can have zero height, and up to all and any width. I mean, read pixels from copy. You can read pixels from. This is just getting really confusing. I don't know if this is. So they have copy index I index j is equal to image index I index j. So copy is the same thing. So if you go to copy, so we need to check the surrounding values. So how can we do that? We need to iterate over another matrix, a submatrix basically, across that. So here you're at 1, 1. And so you'd go I don't know. How would we know that this value exists? So if I is greater than 0, so if I or j are greater than 0, if I and j are greater, we're in an internal node and we can do this whole evaluation. But if I or j is equal to 0, we're on an edge case. So we'll say if I equals to 0 or does not equal 0 and j does not equal to 0, right? We can do this entire thing, right? So copy can when implementing blur function, you might want to then create a new two-dimensional array with code like RGB triple copy, height, and width. Then can copy image into copy. Oh, because they're creating a copy basically. They're going RGB triple copy height. Okay. Width. So they're creating a copy of it, of the entire RGB triple, a blank copy that we can fill in. You can copy in. we're copying every value into copy. Now you can read pixels from copy, but write onto the image. For int I row minus 1. Well, row will be -1. Row will go up. Column. Then you do image at -1 plus the column plus -1 plus the row. 0, 0. Because you still want to blur j equals 0, so you check the submatrix is in domain or not. Okay. So we created a copy of the RGB triple of the image, basically. We have a copy of the image. How can we... So if I, for height, is not 0, meaning that we're at one of these categories, and j is not 0, so meaning we're inside of here, j is 0, height is 0, is these ones. Or so it should be height if I equals 0 or j equals to 0. My brain's hurting. So we can say for int row -1, while row less than equal to 1. Oh, are you saying on top, not in this loop, because we... So we're gonna need to loop again, basically. So for int row equals -1, -1, 0, 1, while row is less than or equal to 1. Yeah, row plus plus. Okay. Then we say for int column equals -1, column less than or equal to 1, column plus plus. Okay, so now we're accessing the row and column. If I so we want to say I plus row. We want to read off copy image I index j. So that gives us the pixel dot RGBT red. This will be plus row plus column, so that's height, plus row copy plus row RGBT red. So we're getting the access to the red one, getting access to copy index I plus column. Let's just duplicate this line, I guess, twice. Make this blue, make this green. So then we're iterating over all of the, so if we're on 1, 1, we're iterating over I minus 1, which would be I plus negative 1, so 0. I'm going to save this value here at each step. Copy. Oh, shoot, I don't know how to do this math. So we are accessing each value and copying them over, right? So we have two matrices, copy and image, with all the same pictures. We then access the surrounding ones in a 3x3, get the red, green, and blue from each square, say average, say red, int green, int blue. then we go red plus equals copy, blue plus equals copy here, green plus equals copy here, like this. So we're going to add red, blue, and copy. And then we need to average out those copies at the end of the loop and save that value. So int average red equals red divided by 9. Int average blue equals blue divided by 9. Int average green equals green divided by 9. Initialize my accumulators. Are these not initialized here? Oh, as 0? So we'll set these to 0. Accumulate all of the red, blues in that sub matrix, average them out, and set image index I and index J dot RGBT red is equal to average red, and then do this twice more for the blue and the green. All right, and this will be blue. This will be green. Now that'll work for all the middle cases. Now what about the edge cases? Right? All right, I'll stream for about 5 more minutes, you guys, and then I gotta head out here. But I'll be back potentially later this evening for maybe just a live coding session, just doing some work on the project, the small business manager, with some chill music in the background or something. I'm going to go see a movie. There's your problem. So we'll copy all of them first outside of this loop. Like so. We copy the entire thing. What time is it for me? It is 6:40 right now. Gotcha. So we copy the entire thing. Row equals -1. Row equals I. Okay. I get you. So we copy the entire thing. Then we make this submatrix. So at I equals copy at I. Well, we don't have I initialized anywhere here. Right, we have I here. Which I don't think it's supposed to be in here. Right? Line 85. Okay, let's take this for loop. And put it here. No. Here. That. Yeah, so we go over the entire copy again. Height, width. We access. So we say we loop over the copy now. Get red, blue, green for each submatrix. So we loop over the copy matrix, right? We do a submatrix loop over this one, so we'll go 0, 0. We'll access -1, -1. So we need a catch here, though, that says if I is 0 or j is 0, to don't do anything. Because it'll try to access copy at 0 or -1 plus 0, which will be -1, which will throw us an index error. Right? So if I is 0, column is -1, that'll throw us an index error. So it'll be -1, -1. So we need to say you need to check in the for loop on 106, right? If I plus column if I plus column less than 0 or If I plus column is less than 0, or I plus column is greater than height, right? If j plus row less than 0, or j plus column, j plus row greater than height, hey Roa Code, how you doing? Welcome. Hey hardcoreism, how's it going? Welcome. We can be greater than or equal to height. We want to be height as well. No, we can do height. 0 index. 0 index height. Or so we want to stop on 5. Yeah. Then what? This means that we're on an edge case. So are we in a corner? If I plus column is less than 0, or I plus column is greater than or equal to the height, we're going to, I gotta get going, you guys. All right, this is gonna have to be it for me. I'm gonna have to pause here. We're gonna have to try this again, either later tonight or tomorrow. Thank you guys so much for joining me today. I will be back tomorrow or later tonight. I'll send an announcement in my Discord. If I come back tonight, it'll be just for like a working session on our project, the small business manager, just doing some live coding or maybe some practice problems in NeetCode. Just pretty chill. But we'll take a stab back at this probably tomorrow. But I really appreciate you guys joining me. We need to figure out how to handle these edge cases. Instead, do all in a if and pass, and say pass. All right, guys, I got to get going for my movie. So I will talk to you guys later. I'll see you guys later. We can try again later tonight if we have some time when I get back. But I will talk to you later. See you in, sorry, I'm saying that over and over again. Join the Discord for an announcement for my stream so you know when I'm coming live. But I stream every day anyways. But if I do a double feature, it'll be announced in the Discord. But thank you guys so much for joining me. This was Harvard CS50X, week 4 on memory. We finished the problem volume, and now we're working on the less comfortable filter, and we will eventually get to the more comfortable filter and recover after that. So we are implementing these right now. We're almost there. Thanks so much for coming in. I will see you guys in a short little bit. Thank you. Bye. Oh, and feel free to subscribe and follow along to the channel if you want to connect and stay connected. Thank you guys. I'll see you later.